you take a closed subset of a compact set, it must be complete, right? Because they're compact. Oh, nice. So in particular, Cantor sets are complete, right? Example, Cantor set. That's closed. The standard middle thirds Cantor set is complete also. And as another corollary, we should mention that Rn is also complete. And it's basically easy to justify because they are, in fact, Cauchy sequences are bounded, and bounded, they'll live in a bounded subset of Rn. So let me just write the proof idea. If Xn is Cauchy, it's bounded. Did we show that last time? I'm trying to remember if we showed that last time. But if not, can you see how to show it? Picture points are getting close to each other. Yes? So you give me an epsilon. Past some point in the sequence, all the terms are within epsilon of each other, right? So maybe past some point in the sequence, all the terms are within epsilon of each other. Therefore, only finally many are not. So then basically take one of these things and look at the distance to all the points outside and take the maximum. And that with epsilon, right? It is bounded. Why? So here, I don't care. Take epsilon, let epsilon be 1. Or just to be interesting, let epsilon be 17. Okay. Then there exists an n such that the distance from xn to xm is less than 17. For all, such that for all n and m bigger than big N, this distance is less than 17. So I don't care which one you pick, just pick one that's beyond xn. So consider, so let R be the maximum of the distance from x sub, let's say, big N to x1 through the distance from x sub big N to x sub n minus 1, add in 17, and this claim everything is within this ball. So the sequence is bounded by a ball of radius r around x sub n. There. Okay. If it's Cauchy, it's bounded. If it's bounded, it's in a ball. If it's in a ball, it's in a, you could just make it, put it in a closed ball or a closed K cell. So it's in, so this ball is in some K cell in Rn. So this ball is complete. So this xn converges because the ball is complete, because the K cell is complete. Nice. So what have we just done? We've shown that if it's Cauchy, it converges. So this shows that, in fact, Rn is complete. Nice. Okay. Any questions? Yes, Drew. Are products of complete spaces complete? If it's a finite product, yeah. If it's an infinite product, we haven't talked about what an infinite product is, but you have to be very careful. Okay. Excellent. So what's this mean? What this means is, in the space we care most about, Rn, to be Cauchy is the same as being convergent, right? So I don't need to know what the limit is to show that a sequence actually has a limit. So let me just give you an example. Suppose I want to look at this sequence. Xn is the sum of the first n reciprocals. Does this converge? Would you agree that this is a sequence? The first term is 1, the second term is 1.5, third term is 1.83333, fourth term, etc., right? Now, if you just write out the first few terms, it's unclear whether it converges or not. I know you know the answer to this, but if you're just looking at on the face of it, I mean, come on, this thing is like growing really, really slowly, right? In fact, you know, you're going to have to go very, very far just for this thing to get bigger than the number 4, right? So it does, it does this. Okay, so it just takes a long, long time, right? So, you do this at a rate of 1 per second. It'll take, a century for it to actually get past this point on the board. Right? Okay. Does it converge? How could I tell if it converges or not? Well, I could ask, is it Cauchy? Right? If I could show that it is Cauchy, then it converges. If I could show that it's not Cauchy, then it doesn't converge. And we say diverge. Right? It diverges. Okay, so this is what's cool. Check this out. Let's look at this difference. This is, in fact, what I'm interested in looking at, the distance from xn to xm. This is brilliant idea. Look at the difference. What is the difference between the sum of the first n reciprocals and the sum of the first m reciprocals? If let's just say n is bigger than m. What would you say that difference is? It's just the sum of the reciprocals from n to m, right? From the n plus 1 thing, perhaps. So maybe go m plus 1 plus 1 over m plus 2 plus ... through 1 over n. Would you agree that that's what that difference is? Oh, but wait, what's that? Would you agree that this is, in fact, I can take off the absolute value if I assume one is bigger than the other, right? Would you agree that this is at least as large as n minus m over m? Let's see, do I have that right? How many terms are there? There are n minus m terms, yes? And would you agree that each such term is bigger than 1 over, should this be an n here? 1 over n. Would you agree with that? Yeah? Okay, that is cool. Well, what's this? This is 1 minus n over m. Oops, m over n. Right? Okay, so check this out then. Look, if I let m be 2m, you can't stop me from doing that. If I go twice as far out, then what this is saying is x sub, m is bigger than n. Let n be 2m, excuse me. If I go twice as far out, then what do I see? I see x sub 2n minus xn is bigger than what? 1/2. And that's true for every n. Does this sequence have any hope of being Cauchy? No, it can't be Cauchy, because as soon as you let epsilon be less than 1/2, you will never find a point in the sequence beyond which all the terms are closer than 1/2. Because I've just shown you pairs of terms infinitely far out as you'd like to go, where they're bigger than 1/2. Sequence is not Cauchy.